Welcome back, friends. JK, would you be willing to give us an opening prayer today?
Dear Heavenly Father, we're so grateful for this day. We're grateful for this opportunity that we have to be here in class. We pray that Thy Spirit may be with us so that our minds might be open to the concepts that we're learning. We're so grateful for our professor, and we pray for him and his family. Please bless that we'll be able to remember our Savior Jesus Christ and these things we say in Jesus Christ's name. Amen.
Thank you. Okay. I was asked if I would start today with a brief discussion of what torque is all about. And I would suggest the example of the door. When you go to open a door, you just instinctively go as far away from the hinge as possible to push, because you know that that's the way it's going to be easiest for you. If you push far away from the hinge, you don't have to push as hard to get the door to open. I would encourage you today, the rest of the day, every time you get to a door, try pushing just this far from the hinge and see how tired you are at the end of the day. Okay. The further you push away from the hinge, the greater that force is going to be able to cause rotation. The greater rotation it will cause for a given force is another way to say it. Now, we're going to work some torque problems in just a moment. Let's start by making some announcements. Sam, could we hand out these? Who would be willing to help me over here? Thank you, Josh. Okay. What we're handing out are exam preparation sheets. And what you'll notice right on the top is that this exam doesn't open next Friday. It opens next Wednesday, 2 days early. Now it's going to stay open clear until the following Tuesday. So it's going to be open for a whole week. And so everyone should find a time when they feel comfortable taking that exam. Now, our reason for moving up the start date was that some of you expressed that you didn't really like learning new material when you were still studying for the old material for the exam. And so this gives you an opportunity to rush right in before we've gotten very far into the new material and get that test over with. Now, in my guts, I have a feeling that some of us will still wait until the following Tuesday, but that's your decision. You're grown-ups. I will be here in this room next Tuesday evening, 7 o'clock, to answer any questions you might have. As always, we will record that and post that to YouTube and give you the link. Are there questions concerning the exam? The material covered today will be on the exam. The material covered next week will not. Okay, so this is the last day we will be covering material on that exam. Okay, let's take some attendance real quick. Okay, now you can click. Okay, last call. Get your attendance points. Okay, we're here. Now, let me remind you, 95% of the time, a torque is just a force times the distance to the pivot. But they've got to be perpendicular to each other, okay? And 95% of the time they are. Now, if you turn that exam preparation sheet over, you'll see the three different ways that we can find the torque in that 5% of the time when they're not perpendicular, okay? And you'll practice those in today's lecture. This is a scam likely, they say.
That's right.
Just, I'm sorry. It goes off in my hearing aid, so even though you can't hear it, it's driving me crazy. Which is not a long drive. So, like I said, you will be practicing those different methods in this week's tutorial. Some of you today, some of you tomorrow. And you'll find when it's useful to use the useful force method, when it's best to use the lever arm method. Thank you. Let's figure out how to solve these torque problems. Back when we were talking about linear equilibrium, when acceleration was 0, you had it down. If this block had two forces to the right and one force to the left, and I told you that the diagram for it needed to scream balance, you could instantly tell me how big that force to the left was. You would just say all the force to the left balances all the force to the right. Easy peasy. Well, the same principle is involved when we're looking at torque. Now, we looked at this picture at the end of last day. Let me just explain it a little bit better. We have a pole here that is very, very strong, but very, very light, made of graphite epoxy or something, so that we can neglect its mass. It's forced to pivot right here. There's a really, really good hinge right there, and this bar can rotate about that hinge. Now, if I just hung this 200 Newton mass at the end, that would flop down to the floor, bringing the pole with it. Just, okay? You visualizing this? But if I don't want it to flop down to the floor, I've got to pull up with something. And if I pull here a quarter of the way down that pole, the question was, how hard do I have to pull? And to do that, I would use the fact that it has no angular acceleration. If it's just sitting there, not rotating, alpha is 0. And we found last day that it's the torque that causes the alpha. So that means if there's no alpha, there's no torque. Another way of saying that is that all of the torque that's trying to make this pole rotate clockwise has to balance all the torque that's trying to make it go counterclockwise. So what we do is we remember that there's a hinge there, and we ask, if this was the only thing pulling on that pole, would it go clockwise or counterclockwise? It would go clockwise. If this spring scale were the only thing pulling on that pole, would it make the pole go clockwise or counterclockwise? It'd be counterclockwise. And so that means that this 200 newtons times the distance to the pivot has to equal this force times its distance to the pivot. And sure enough, 200 times 1 is equal to 800 times a quarter. Check on your neighbor, do a buddy check real quick.
So far, good job. Right. So I also actually, I know, she made.
Like if it was something like.
Okay,
Got it.
let's practice some more. Last day we had this setup where we had these two spring scales supporting this 1 kilogram bar that was a meter long, and 1 kilogram mass was hanging from it 80 centimeters from the left. And we knew that the reading on the spring scale on the right had to be bigger than on the left. There was a heavy end. But when I asked you to predict the readings on those two scales, 28 of you got it right. Now, everyone, look around. Okay, there's 280 students in here. Okay, there's supposed to be 340, but there's 280. Okay, that means we were confused. That means we were not ready. We didn't have the tools we needed, but now we do. Now we do. So let's solve this problem. Okay. We know that the acceleration of the center of mass is 0. It's not going anywhere. So we know that all the force up has to balance all the force down. And sure enough, we knew that the reading on the spring scales had to add up to 20, because I've got a total force down of 20 newtons. Okay. But that wasn't enough. The fact that it's not angularly accelerating told me that the net torque had to be 0. Namely, that the torque clockwise had to balance the torque counterclockwise. Now, we're looking for the force exerted on that bar by the spring scales. So what we're going to do is draw a free body diagram for the bar, because we're looking for forces on the bar. But not just a regular free body diagram like the olden days where we put a dot representing the center of mass. No, we have to draw the bar, because where the forces are applied is critical. The first force that we put on any diagram is always the gravitational force, the weight force, and we always, every sinking time, put it at the center of mass. Now, you're going to be tempted later today to put it somewhere else. Don't give in to temptation, okay? That was our devotional today. Then I ask, are there any magnets in this problem? No, but that would be interesting. So what touches this bar? Well, I've got that 1 kilogram mass pulling down with a tension force of 10 newtons. And I have the two spring scales pulling up. Now, before I can balance the torques, I have to put a pivot point. Okay, without a pivot point, the idea of a torque is meaningless. But where do I put my pivot point? Well, it turns out that because this is not rotating about any point, you can put your pivot anywhere. I can put it here, 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 I can put it there, I can put it there, I can put it in a point in Kansas and get the same right answer. However, if you don't really enjoy solving two equations and two unknowns, there's only two smart places to put your pivot. Only two. I can either put it here to eliminate this unknown from my equation, or I can put it here to eliminate this unknown from my equation. Let me show you. If clicker's not working. There we go. Now it is. If I put the pivot here and balance all the clockwise torque with the counterclockwise torque, again, I play an imagination, a mind game. I pretend that there's a big golden spike through that bar right here. Like a hinge, forcing the bar to rotate about this point as if this were the hinge on a door. And then for each of the forces individually, I ask, is this force trying to make it go clockwise or counterclockwise? Well, first of all, this one is pushing at the hinge. That's not going to cause any kind of rotation. That's why I put the pivot there, is to get rid of this unknown force. This force is trying to make the bar go clockwise. This force is trying to make it go clockwise. This one's trying to make it go counterclockwise. So if I look at the balance here, I have this 10 Newton force times its distance to the pivot. I then add this 10 Newton force times its distance to the pivot. And that has to balance with this unknown force times its distance to the pivot. When I solve that for the unknown, I get 13 newtons. Again, that was a choice that 28 of you chose last day. Some of you may have chosen that just by chance. Okay? I know that all the force up has to balance all the force down. So this has to be 7, because 7 plus 13 is 20. Yes, sir. You want me to move it over to the other side? Just right now, on the fly? Just right now? Just because?
I'm asking if like that works for you.
Jeff wants to, I'm sorry, Josh wants to do it this way. Oh, thank you. You set me up. Let's do it again. Let's put the weight down, the force down, these up, and let's put the pivot over there. Whoa, great minds, great minds. Okay. Okay. We could have chosen the pivot over here. Now, when I balance all the clockwise torque with all the counterclockwise torque, I get different clockwise and different counterclockwise. Again, I pretend there's a big golden spike here forcing this to be the hinge. Well, now, this force is trying to make it go clockwise. This force is trying to make it go counterclockwise. This force is trying to make it go counterclockwise. And so my equation looks very different than it did last time. The clockwise torque is this unknown times its distance to the pivot. I have this 10 Newton force times its distance to the pivot. And then I have this 10 Newton force times its distance to the pivot. And because this one is acting at the pivot or at the hinge, it gives me no torque. It's like pushing at the hinge of the door. Okay. And now when I solve for that unknown, I get 7 newtons. Again, it all has to add up to 20. So I get the same answer as before. Good or very good? Okay. So, questions on that? Yeah.
Will we always be solving torque for whether to go and?
The equilibrium problems will always have no acceleration. Yes, we are going to deal with the cases where there is acceleration later in today's lecture. Yeah. Okay. You have this homework problem, problem 4 in the homework due tomorrow night. In my textbook, there's all sorts of Bob and Will problems. They're brothers. And Will never really carries his full load. He kind of doesn't like to exert himself. And so Bob and Will have found a very clever way to transport their lunch to work. They use this 71 kilogram beam to carry the lunch. And the question is, how hard does Bob have to push up on this beam? And how hard does Will have to push up on that beam? Well, your gut's telling you that Bob's pushing harder than Will. But how much more? Well, again, we're looking at pushes that are exerted on the beam. So we draw an extended free body diagram for the beam. Now, the first force we put on any diagram is going to be the weight force. Because it was 71 kilograms, that weight force is going to be on Earth, 710 newtons. And the beam, remember, was 2 meters long. Now I ask myself, are there any magnets in this problem? No. Be patient. So what touches the beam? I've got this tension force of 200 newtons at the end supporting the lunch, and I have Bob and Will that are pushing up. Now again, because this beam is not rotating about any point, I'm free to choose any point as the pivot. But again, if you don't like math that's really complicated, there's only two smart choices. Right here to eliminate this unknown, or right here to eliminate this unknown. Let's choose the pivot to be right here. If I balance all the clockwise torque with all the counterclockwise torque, again, I pretend that there's a big golden spike forcing this beam to rotate about that point like it were the pivot or the hinge on a door. This normal force by will gives me 0 torque. This one's trying to make it go clockwise. This one's trying to make it go counterclockwise. This one's trying to make it go clockwise. Okay? I set up my equation, and here I have a very tragic story to tell. So for the clockwise torque, I've got this 710 newtons, and its distance to the pivot is 1 meter. I have the 200 newtons also trying to make it go clockwise, and its distance to the pivot is 2 meters. My tragic story is that this is an old exam question, and a good chunk of the class got it wrong. And why did they get it wrong? Well, I blame me, because I put this picture on the exam. And because I labeled this distance right here, they put 0.6 meters right there. Sick and wrong, or just regular wrong? Sick and wrong, yeah. Okay, sick and wrong. It's the distance to the pivot, regardless of what we label on the drawing. Now, when I solve that for the one remaining unknown, I get 793 newtons. Well, all of the force down has to be balanced by all the force up. And if I add 117 to 793, I get 910, which is the total force down. Please talk to your neighbor. Talk to your neighbor.
I don't want to know how to.
Yep.
That's it. A little bit much. Talk about the math.
What questions do we have? Any questions? Okay, let's see if we understand what's going on. I have a very special meter stick, and this meter stick was designed just so that if I hang a 1 kilogram rock right from the very end at the 0 centimeter mark, I could balance it at the 25 centimeter mark and it would remain perfectly horizontal. it has just exactly the right mass to make that balance. Now with your neighbor right now, figure out what the mass of that meter stick is. What's the mass of the meter stick? Go with your neighbor.
Because mass balance.
Body diagram.
Mine then.
At halfway, no.
Stationary.
I'm so sorry.
That's the question that he's like.
Mine, five.
Go on, yes, I'm. Learn.
No idea. But you can ask, there's nothing else to do. A meter.
Hash mark is one, hash marks.
The center mass of the meter.
Okay, there are likely an infinite number of answers in the room. Finite, infinite. But all of your answers are gonna fall into one of three bins. Either you came up with an answer that was less than 1 kilogram, or you came up with an answer that was equal to 1 kilogram, or you came up with an answer that was greater than 1 kilogram. With your clicker, tell me which of those bins your answer belongs in. With your clicker, please.
Sorry, I think I should understand. One times. So I don't know.
This is pushing up.
Okay, last call, people, get your vote in. Okay, greater than 1 kilogram is the winner if this were a democracy, but it is not. It's a science class, okay? So let's work this together.
I don't know. There's not gonna be it.
No, that's the thing, like you wouldn't know.
Okay,
That is.
now we're looking for the mass of the meter stick. And we know that the earth pulling on the meter stick, the weight force, is just the mass of the meter stick times G, where we always approximate G is 10 newtons for each kilogram. So if we could find the weight force, we could find what we're looking for, which is this mass. Well, let's draw an extended free body diagram for this meter stick. And I'm going to do my best here. There's 50 centimeters, 25 centimeters, 75 centimeters. Now, what forces do I put on that meter stick? Well, the first force I put on any free body diagram is the gravitational force. And I always, every sinking time, put it at the center of mass. Now you're thinking right now, but Greg, part of that meter stick is to the right of the pivot and part of it's to the left of the pivot. I assure you, the earth don't care, okay? It pulls the same with or without that pivot point there. Always at the center of mass, always at the center of mass. I then have this string pulling down, and because it's supporting a 1 kilogram mass, I know from a free body diagram of the rock that that is going to be a tension force of 10 newtons. I then have the pivot force up, the normal by the pivot on the meter stick. Now, before we can balance our torques, we have to choose a pivot. Where should we put our pivot? And I know what you're thinking again. You're thinking, Greg, there's a pivot. We can see it. It's right here. Yes, that's the physical pivot. But I want to choose a mathematical pivot that I'm going to balance the torques about. And because this meter stick isn't rotating, it's not accelerating in a rotational way, I can pick any point to be my pivot point. I choose this point here. Not because that's where the physical pivot is, but because I've got two unknowns. Nope, nope, nope. Two unknowns. And I don't care about that one. This is the unknown I'm looking for. And I don't want to solve two equations and two unknowns. So I put my pivot here to get rid of the unknown I don't care about. You understand what I'm saying? Okay, it just happens to be where the actual pivot is located. And so now if I balance all the clockwise torque with all the counterclockwise torque, this is trying to make it go counterclockwise. This is trying to make it go clockwise. This one's pushing at the pivot, no torque. And so the clockwise torque would be the weight force that I'm looking for times its distance to the pivot. That's going to be 25 centimeters. Or we always put it in meters, don't we? And that has to equal the counterclockwise torque, which is 10 newtons times its distance to the pivot. And that's going to give me a weight force of 10 newtons. And that gives me a mass for the meter stick of 1 kilogram. Now, folks, if you're still bothered by the fact that part of that meter stick is to the left of the pivot and part is to the right, I suggest a little exercise that will take you most of the afternoon. Pretend, if you will, that this is two sticks, a left stick and a right stick, okay? And they're glued together right there. Think of that as horizontal forces. And then treat them as separate objects. Put the weight of the left side there and put the weight of the right side there. And you know that the total weight of the meter stick is going to equal the weight of the left side plus the weight of the right side. Work it all over again, and what you're going to find is, after a lot of mess, 1 kilogram, I promise. Okay, check on your neighbor again, people. Check on your neighbor.
Forgot about that. Sounds like it. I need to talk to.
Okay. Are we starting to see that all of the equilibrium problems are pretty much the same? We draw an extended free body diagram. We choose a pivot point to get rid of one of the unknowns. We balance all the clockwise torque with all the counterclockwise torque. And then finally, we use Newton's second law to find the unknown that we eliminated. Okay. We have just a couple of more concepts that we need to understand before we're ready for that exam next week. And I'm going to teach this in what is perhaps one of the most ineffective ways possible, okay? This is the only time during the semester that I'm going to use analogy. Our Savior got away with it over and over again with his parables, but you remember that a lot of the people didn't understand those parables, and that was why the Savior often used them, was to protect those that weren't ready for the truth, so that they wouldn't be responsible for the truth. Well, I'm not trying to protect any of you from the truth in here, but I'm still going to use parable or analogy, in my case, just because I'm running out of time. Okay, so let's do it. When we were talking about linear motion of the center of mass, the one rule, the one equation to rule them all and in the darkness find them was Newton's second law, and it applied to the center of mass. Now, just like a net force causes, that's what that equal sign means. A net force causes a mass to linearly accelerate. We found that a net torque causes a mass to angularly accelerate. The question is, what's that constant of proportionality? Is it the mass or is it something other than the mass? And that's what we need to explore really quick here. I need some volunteers. Thank you and thank you. Come on, Josh, get up here. Okay. Yeah. Okay. Sydney? What's that?
Alexia.
Alexia,
Yeah.
not even close. Sydney's over here somewhere. There's, okay. Josh, okay. Now, what we're gonna do is we're gonna play dueling batons. And this is a new Olympic event. You may not have heard of it. Are you right-handed? Okay. I'm gonna give each of them a baton, and when I say go, they're going to try to rotate their baton just as fast as they can. And the one that does it faster is going to be the winner. Okay? Are you ready? On your mark, get set, go. Oh, it looks like Alexia's winning there. Let's just hold on. Let's we know that these are sometimes rigged, so let's switch up and do it again. Okay, now. Oh, Alexi's having a trouble there. Okay, let's give him a hand, folks. Now. Oh. Come back. Okay. It might surprise you to find that these have exactly the same mass. If I were to put them on some sort of scale, they would have exactly the same reading. However, this one is very, very easy to rotate. And this one is very, very hard to rotate. If mass were the only thing that determined how easy it was to cause an angular acceleration, then mass would be the constant of proportionality in that equation. But it's got to be more than the mass, okay? Now, it turns out that with this rod that has the same mass as this rod, all the mass is located right here, close to the hinge, close to the pivot, and it's easy to turn, okay? With this rod, it has the same mass, but it's out here at the ends, so that it's hard to turn, okay? And so that makes it more difficult. Now, it turns out that mass is not that constant, that the constant is more complicated. And we use the symbol capital I for it. And it turns out that that capital I depends on both the mass and also on the size of the object. And we call this the moment of inertia. And it's called moment of inertia because of a term in calculus that we're not going to worry about because we didn't take calculus before this class, okay? It turns out that this constant, this B, is different for every shaped object. And when I was young like you, I had to memorize this table where I had to remember that that B was 1/2 for a disc, it was 2/5 for a billiard ball, it was 2/3 for a wiffle ball. Everything had a different value for B. Do not be writing that down, people. I would never, ever force you to memorize that table because it scarred me, okay? I don't want you to be scarred like I am, okay? Now, the important thing to remember is just that you can change the moment of inertia by changing where the mass is located, Now, imagine, if you will, that you're at a circus. And at that circus, they have a high wire act, okay? And on that high wire act, maybe there's a trapeze artist that is just up there doing this, okay? That's an experienced pro. Respect, okay? And then you've got someone that's got a really, really long pole, goes out on both sides. And that person, well, he or she's still pretty new at the job. And if you see one that's got a long pole with weights at both ends, first day on the job, okay? Now, why is that easier to have that long pole with the weights at the end? Because that pole with the weights at the end doesn't want to rotate. And so if you're walking along the wire and trip and you're falling, just grab that pole and pull yourself up. It's like it's stapled to the sky. It's like training wheels, okay? Now at that same circus, there's usually a group of brothers, the Linguini brothers, and they do an act where the oldest Linguini brother has a big long pole with a chair on the top. And they put the youngest Linguini brother in the chair, and then the oldest brother takes that pole with his brother and puts it on his forehead and balances on its forehead, knowing that if he drops his brother, he's in serious trouble with mom, okay? Now the pole's long, and the longer the pole makes it harder or easier to balance. Easier. If I get that mass further away from the pivot, my forehead, it's going to be easier to rotate. Let's, I keep picking on you, Austin. Come on up. Let's demonstrate that. We're going to have Austin balance this where the mass is down low, and then again when it's up high, and tell us which is easier. Oh, you're pretty good. Okay, now try it the other way. Which was easier? Okay. We need to put more mass in that ball then. If we had this filled with lead, he would find it much easier this way, where the mass is further away from the pivot than this way. And indeed, when I do it, I can't even do it that way. You almost got hit with something, and then you would have we would have owed you a lot of money. Okay. Let's move on. When we were dealing with linear motion of the center of mass, we encountered this concept that if we could isolate the system so that there was no net external force, that there was this quantity called momentum, linear momentum, that was conserved, that stayed the same, regardless of how messy the interaction was. And that linear momentum we found was the mass times the linear velocity. And those are vectors. I didn't put the arrow sign over there. I was in a hurry. But momentum and velocity are vectors and in the same direction. Now that means if you step outside the space shuttle and you get yourself going, unless you've got some sort of a propulsion pack on your back, you're not coming back. You're just going to keep on going at the same speed forever. Now with rotational motion, instead of isolating the system so that there's no net force, we isolate the system so that there's no net torque. And if we can do that, then there's a quantity that we call angular momentum. For historical reasons, we use capital L to represent angular momentum. Now, if linear momentum is mass times linear velocity, what do you think the formula for L is? What would I use instead of M? M is how hard it is to get something going down the road. What tells me how hard it is to get something going around the wheel? I. And instead of linear velocity, I would have angular velocity, okay? And these are vectors. And so what this means is that once something's moving in a linear way, it wants to keep moving. Once something's rotating, it wants to keep rotating. Now I can demonstrate that with this gyroscope, and I'm going to do something that if everyone would give Clark a hand. He's the one that takes care of all of our demo equipment here. And he's going to be appalled at what I'm going to do right now. I'm supposed to use a string to get this going. But I'm lazy. Okay, now what direction is the omega vector for that wheel? Use your right hand. Yeah, it's right out that pole, isn't it? Okay.
Sure.
Now, if I can isolate this so that it has no net torque, and I've done that with these weights over here, then once we've established that angular momentum, it wants to stay the same. That wheel wants to keep turning the same rate and pointing the same direction. Now that means that I can pick up the base and I can go all over the room, do a little dance, and it just always keeps pointing the same way. Now, those of you in ROTC, what might you do with something like that? Yeah, you put 3 of those in the cone of a SMART missile, one of them that's pointing east, one that's pointing north, and one's that's pointing up. And then no matter where your missile goes, it always knows where east is and where north is and where up is. And it can follow a digital map down that little canyon, and we got bin Laden. Oh yeah, been there, done that. Okay. Now, if the external torques are not balanced, and I can do that by putting this little weight at the end here, what we see is what we saw last week. Okay. And that's precession. Okay. And that's because there's an unbalanced torque that's causing, in this case, an alpha that's pointing this way, the way the omega vector is going. Okay. Now, another demo that I can do. Okay, now. What direction is omega pointing now? Up, okay. So right now, if I sit on this chair that's free to rotate, I'm getting rid of all the external torques. Now, the angular momentum of the system of me and this wheel is pointing towards the ceiling. If I force the angular momentum of the wheel to point towards the floor, I now have to compensate by having an angular momentum up. Now, folks, that's how we make spy satellites. I want to look over here. Whoa, yeah, look what they're doing. Whoa. Okay. Now, let's put this back in its cradle. Okay. Ouch. Don't do that. Okay. Now, there's a big difference between this angular momentum and the linear momentum. And that is, you can't change the mass of something easily. But I can change the moment of inertia easily, okay? If angular momentum has to be conserved, if I eliminate all the torques, then I can change my spin rate by changing my moment of inertia. Now remember, moment of inertia depends on where the mass is located relative to the spin axis. Now, when you see those figure skaters go into a turn, into a spin, they always go in like this, only a little bit more gracefully, okay? And once they get spinning, they pull in their arms to go really fast, Now we can demonstrate that. Clark, would you sit on that stool for me? Okay. There you go. Let's make sure that you're not going to hit anything there. Okay. Okay, you ready? Put those arms out. Oh, yes, I do.
You know how much I don't like this.
Oh, okay, let's do it the other way. I'll do it the other way.
Stay cruel.
You spin me. Oh, yeah. Oh, you. Yeah. Oh, man, make me go fast. That's fast enough. Okay. So, that demo has not always gone well. Many years ago, I was teaching at University of Washington in Seattle, and I was doing demos with a bunch of second graders. And I got one of their teachers up on the stool and asked two of his little students to come to spin him. And just as we were about to get started with the demo, one of the other teachers asked a question, and I walked up and started answering the question and didn't realize that the two little kids were spinning their teacher. And before I could say anything, he pulled in his arms, went spinning around, flew off the chair, broke his glasses. He was okay. He could have sued the university, but he was a second grade teacher and they have hearts of gold. So we were okay. See if your neighbor understands this idea, okay? See if they understand how to solve a figure skater problem on the exam. So. Thank you, Clark.
Got it out.
Slow or that has to be the eye.
So if you decrease it to that.
A large moment of inertia because the mass was further away from the spin axis. when I pull it in, I get a small moment of inertia.
Bye.
Well, it's that formula B M R squared. The R is how far it is away, and that's squared.
Oh, shoot.
Yeah. But that's why it covers.
Okay. Let's look at, are there questions before we move on to some more torque problems? Okay, yes, sir.
Lucy's blade in it.
Well, that was the case.
Lifted, like one way you weren't moving, and then when you flipped it, you were.
Certainly, yes. Let me. Let me use the board here. If I put that blank, thank you, Sam. When I was first sitting down on the wheel had an angular momentum. When I was first sitting down on the chair, rather, the wheel had an angular momentum up, and the Greg wasn't spinning. There was no angular acceleration, or angular momentum, rather. So when I forced the wheel to be upside down, now the angular momentum of the wheel pointed towards the floor. But it's just like when we were talking about linear momentum, it wasn't the linear momentum of block A that was conserved, or the linear momentum of block B that was conserved. It was the momentum of the system combined. And so that means that the momentum of the system, which was just this before, because Greg contributed nothing, the momentum of the system still had to be what it started out. And that means that the momentum of Greg had to be what I had to add to this to get me that. That's going to be the momentum of the Greg. And so that's why I started spinning the same rate, the same direction that the wheel was originally spinning. And because I have so much mass and I don't want to talk about it, I didn't have to have as big a spin rate to get a big angular momentum. That answer your question? Okay. Okie dokie. Folks? Yes.
Talk about why I failed.
He's saying it's still.
Look this up. Ice skaters spend as much time on their upper body strength as they do on their lower body strength. I literally did not have the upper body strength to do the work.
To pull it in.
Goes in, even if I wanted to, and I was losing my balance, but
We lose our balance, don't we?
there's a lot of things.
Okay. Folks, this is the torque problem that you want to find on that exam. This is the easy torque problem, okay? And this is problem 5 on your homework, but you're gonna have different numbers. We've got a platform that has a mass of 40 kilograms. We have a painter that has a mass of 70 kilograms, and he's standing a half meter away from the right end, and the left cable is tied a half meter from the left end. The plank or the platform is 2 meters long. We're asked in this problem to find the tension in those 2 cables. And our gut's telling us that it's going to be greater on the right. Now we're looking for forces on the platform. So we draw an extended free body diagram of the platform. The first force we put on any diagram is the gravitational force. And because this is a diagram of the platform, not the painter, that's going to be the mass times gravity of the platform. I then ask what touches the platform. Well, I have the painter pushing down. And if I were to draw a free body diagram for the painter, I would find that that normal force was 700 newtons. I then have the two cables pulling up left and right. Now I have to choose a pivot point. Well, again, any point is a valid pivot point, but there's only two smart choices. Either here to get rid of this unknown, or here to get rid of that unknown. I'm going to choose it right there. Now, if I balance all the clockwise torque with all the counterclockwise torque, again, I have to pretend that there's a hinge right there and that this platform's forced to rotate about that hinge. This gives me no torque about that hinge. This is trying to make it go clockwise, clockwise, counterclockwise. So I write my equation. There's 400 newtons times its distance to the pivot, half a meter. There's the 700 newtons times its distance to the pivot, which is 1 meter. And then the counterclockwise is this remaining unknown, the tension in the right cable, times its distance to the pivot, 1.5. When I solve for that unknown, I get 600 newtons. I've got 1100 newtons down. I've got to have 1100 newtons up. So this must be 500 newtons. Does that seem like something you could easily do on an exam? Okay.
Oh my gosh.
This is the problem you don't want on your exam. Okay. Here we have a drawbridge of mass 2,000 kilograms and length 24 meters. And it's supported by two cables on either side of the drawbridge. They're both 8 meters away from this hinge down here. And the question is, if this is sitting at an angle of 53 degrees, why wouldn't it be, relative to the horizontal, how big is the tension in each of these cables? Now, you know the first step. It's the first step for all of these problems, and that's to draw an extended free body diagram. So since we're looking for the forces that the cables are pushing on or pulling on that drawbridge, we draw a free body diagram for the drawbridge. The first force we put on any free body diagram is the weight force. It acts at the center of mass and points straight down towards the bottom of your page or the center of the earth. And because it was 2,000 kilograms, that's going to be 20,000 newtons. Now we ask, are there any magnets in this problem? No, still no. So what touches the drawbridge? Well, I have those two cables pulling. What else? What else touches the drawbridge? Yeah, the wall right here at the hinge, the wall is exerting forces that I don't know. And I don't want to know. Okay, that's the important part. I've been offered $10,000 and an A in the class to find out what those tension forces are. I've been offered gar-nix for these forces. I don't care. I don't care. Now, before I can balance my torques, I have to choose a pivot point. Well, Greg, there's a pivot right there. I see it. I see it right there. Well, here's the deal. That drawbridge hasn't lowered for 2 centuries. I'm not sure it can. Okay. And so I hesitate to even call it a pivot anymore. More importantly, I'm looking for a mathematical pivot, not a physical pivot. And I've got an unknown here, and I've got a bunch of unknowns there. This one I care about, those I don't. So I choose my pivot to get rid of these forces out of my equation that I don't care about. Does everyone see the reason for choosing that point? Okay, now we have to balance all the clockwise torque with all the counterclockwise torque. But before we do that, we have to use some of what we learned in tutorial tomorrow. We're going to have to go forward in time with a time turner. Okay, but you learned it also last Tuesday, and that is in 5% of the problems, this force is not perpendicular to the position vector from the pivot to where the force is applied. In those few cases, and this is one of them, you have two options. One is we can break up that force into what we call the useful part of the force and the worthless part of the force. Think of that blue arrow and that green arrow as ropes, and they're both pulling right here at the center of mass. The blue arrow pulling this way and the green arrow pulling that way, straight down towards the pivot. Okay, I've drawn them like this so that I can do some trigonometry, but both of these ropes are pulling right there, and the green one's pulling right towards the pivot. How much torque am I going to get out of that green force? Nothing. Okay, so it's this one that I care about. We remember earlier in the class that if I think of this as the spike and this is the plumb bob, that this angle is going to be the same as the angle of the drawbridge. And now I can just use my trig functions to figure out that this is going to be 20,000 times the cosine of 53 degrees. Cosine of 53 degrees is 0.6. That gives me 12,000 here. When I balance the clockwise torque, that's going to be due to this force. With all the counterclockwise torque, that's due to these two forces. I get this equation here. There's the force that's trying to make it go clockwise times the distance. Remember, it's 24 meters to there, so it's 12 meters to there. And then I've got two torques here, one for each cable. That's the force times this distance, which was 8 meters. When I solve that for the tension, I get 9,000. Yes.
Assume that the two tension forces are the same.
Oh, symmetry. We're looking at it end on, but if we were looking around at the other end, where this great big, let's say this great big drawbridge is like this, I go up 8 meters on this side and tack it on. I go up 8 meters on this side and tack it on, and then pull them back to the same place on the wall. I have no reason to expect the right side to be pulling harder than the left side. Symmetry. Okay. Other questions? Yes.
How did you know that the tension was 8 meters away?
That was given in the problem.
Oh, okay.
Yeah, and when you solve your homework problem for next Tuesday, you'll get a different number than 8 meters. Everyone gets a different number. Other questions? Okay. Oh, look at this one. Oh. Once we start having fun with something, why don't we just put it underwater, huh? Yeah, hey. Okay. This is also a problem that you'll be solving, again with different numbers. But we have this meter stick, and we find that when we submerge it, we know that its weight is 4 newtons, whether it's submerged or not. That doesn't matter. The water doesn't change that. We find that if we pull down with 2 newtons at this end and pull to the right with 6 newtons here, that we can get this thing to be perfectly balanced so that it's not going up, not going down, not going left, not going right, and not rotating. If we just use one more string, and what we're asked in this problem is, how hard should we pull on that string, and what angle should that string make with respect to the vertical? Now, we know that there's another force on here, and that's related to that water that it's immersed in. And I hope that by this point, we're all really sure how big that buoyant force is because we're told the volume of the meter stick is 300 centimeters cubed. Tell your neighbor really quick, how big is that buoyant force? Tell your neighbor. This should just pop out of your brain. Just boom. Wah.
I don't know. Grams is.
Hundred centimeters. Yeah.
Okay. Everyone that's sitting next to someone who got the right answer, raise your hand. How do you know what's the right answer? The right answer is 3 newtons. Did you get that? Applaud if you got 3. Okay. I was hoping that that would be a little bit more resounding. I don't want you to raise your hand. But some of you are still struggling to see that that's 3 newtons. And I'm guessing that if I had submerged that in heavy cream or alcohol, where the density wasn't 1 gram per cc, more of you would be still struggling with that. So let me ask you a different question. Next Tuesday, I'm going to show up at 7 o'clock to help us get ready for this exam. If I were to show up a half hour early and just talk about basic buoyancy problems, how many of you would find that useful? How many of you would? Okay, that seems like enough that we should do that. Okay. Why don't we, rather than working this to the end, why don't we save this problem till the beginning of day on Tuesday, and hopefully you can review some of these ideas. What's that? I will record it. Yes. Now, folks, one moment. This week's tutorial is a handout. I sent you a digital copy in an email. There's a digital copy at the MAC site under class notes. There are paper copies up here. If you're old school, pick one up on your way out the door. Okay.